Okay, so here's the periodic table that we all know and love. It is arranged into columns based on the number of valence electrons that these atoms have. Everybody in the first group has got one valence electron. Everybody in the second group has got two. And a Russian guy by the name of Dmitry Mendeleev was the first one to start to organize these elements like this. And he didn't know about how many valence electrons they had. He just knew that there are certain properties that these things had in common and that they repeated every so often. You get these properties to start again. There's a trend, a periodic trend with some of these things, like ionization energy or the size of the atoms, the radius. And so he started to organize them into a table, and we've added on to it a lot since then. But this is where we're at now. He only knew about 60 elements back then. We skipped that middle section. Don't worry too much about those. I don't want to give you a rule of thumb for them. Technically, they've got two valence electrons, but there's a lot of exceptions and weird things that happen there. So if we look at boron's group, that family there has got 3 valence electrons. Carbon's got 4. Nitrogen's family, nitrogen, phosphorus, arsenic, what do we got there? Antimony and bismuth. They've got 5 valence electrons. The oxygen column there has got 6 valence electrons. Fluorine's whole column has got 7 valence electrons, and the noble gases have got 8 valence electrons, except for helium, who's only got 2 valence electrons because it would have the 1s2 orbital filled, and that's it for helium. So there's 2 electrons for helium. It's an exception to that rule. So Dmitry Mendeleev is the guy who first organized this thing together, and he put the periodic table together into periods, which are the left to right rows of elements. We call them periods because every period the properties start back over again. The properties cycle periodically, and then the vertical columns are called families. Sometimes they're called groups as well. And families are interesting. Just like your family, you maybe have similar properties. Like people tell me that I look a lot like my brother does. We have similar properties. Elements in the same family in that same vertical group often have similar properties, especially chemical reactivity. And the reason that is because they have the same number of valence electrons. And that's what really governs a lot of the chemistry of each different element, is how many valence electrons it has. So those families or groups are the vertical columns. Okay, so now what we're going to do is what I call periodic table geography. On the periodic table, we divide it up into different chunks and sections that we talk about, and it's important for you to know some of these terms so that when we talk about the halogens, you know where on the periodic table that we're looking at. And so it's kind of like states, and different states have different names and capitals and whatnot, so we're going to learn about some of the geography of the periodic table. So the first thing we should learn about is there's 3 main kinds of elements. And on any good periodic table, there's going to be a staircase drawn in right there. It starts in that corner by boron there and zigzags back and forth. The 3 kinds of elements are metals, nonmetals, and then there's these ones that are kind of in the middle between metals and nonmetals. We call those metalloids, or sometimes you'll hear them called semi-metals. They have a mixture of properties between metals and nonmetals, and they lie right along that staircase. All the elements that touch the staircase are metalloids, except for one. Aluminum, element 13, is a metal. And it's an easy exception to remember because you have a lot of everyday experience with aluminum. You drink out of aluminum cans. You probably have a lot of aluminum stuff at home in the garage maybe and around the house. So aluminum you know is a metal from your everyday experience. But all the rest of those elements that touch the staircase are metalloids. Metals are categorized, they're not recognized by being shiny, solid, at room temperature. They're smooth, they conduct electricity and heat well. And everything to the left of the staircase is a metal, except for hydrogen, which is a gas and a nonmetal. Nonmetals are things that are gases, like hydrogen or oxygen, nitrogen, or brittle solids, like think about carbon as like charcoal. A piece of charcoal is kind of crumbly, it's not very shiny, it's not solid, and it doesn't conduct electricity or heat very well, so it's not a metal. And so it's this brittle, crumbly solid that is also a nonmetal. So everything to the right of the staircase is nonmetals. Now, the metals have got different subgroups inside of them. These are kind of like the states. We have got this first group, they're called the alkali metals. They're very, very reactive because they've got 1 valence electron, and they want to, if they can clear out that 1 valence electron, the level, the energy level, the electron energy level underneath that will be full, and they would have a configuration just like a noble gas, and that's very stable. The group right next to them are called the alkaline earth metals. The alkaline earth metals are also pretty reactive. They get their name because they're found in a lot of rocks and minerals on Earth. They're not as reactive as the alkali metals, but they're fairly reactive. The group in the middle there are called the transition metals. And the group down the bottom are called the intertransition metals. Now, the periodic table that we see most often it's got this separate chunk down here called the intertransition metals. That's the F block down there for electron configuration. And there's no reason why those are down there. They deserve to be up with the rest of the periodic table just as much as everybody else. In fact, if you look at a periodic table the way it really is, it looks like this. That's the way the periodic table is actually arranged, and we suck out those intertransition metals from inside the transition metals, because if we did them like this, if we made the periodic table and we put this on a sheet of paper, all the squares have to be really small to fit, and so the type gets too small to read, and you can't get as much information in it. So we suck that part out in order to make it easier to fit on paper, and that's really the only reason. So those intertransition metals are down the bottom, and then we have this little group just before the metalloids that we call the representative metals, and they are the last ones before we get to the metalloids. Now, nonmetals have also got some different groups. The second to last group there with 7 valence electrons are called the halogens. They are also very reactive. They've got 7 valence electrons, and it's very stable to have 8, and so they go around trying to rob somebody of 1 electron, and so they do chemical reactions very easily because of that. And that very last group on the table is called the noble gases, and I'm sure you've heard of them before. They don't react with anybody because they've got 8 valence electrons. Their outside energy level is full, and so they have no reason to react. They don't want to pick up any electrons, and they don't want to lose any electrons. Now, the main group is a group of elements on the periodic table. Here, I'll circle them in red. That section, basically it's the S block and the P block. Together, if we wanted to summarize the periodic table, there's 120 elements around these days. If we don't want to look at all 120 elements and we talk about patterns, we will sometimes just talk about patterns in the main group. And the reason we talk about them is because they're a good representation of all the elements that are out there. Within the main group, we've got solids at room temperature, liquids at room temperature, and gases at room temperature. We've got metals, nonmetals, and metalloids. We've got elements that are very reactive and elements that won't do anything, that are very unreactive. There's a wide range of properties in here. So this group is a good representation of the whole periodic table in a smaller form. So we call these the main group, or the representative elements.